Now let's go back to our least square lecture. Let's start over again. I think it's been a week. Okay. Now let's talk about least square and the system identification. I think you have the lecture note we handed out last time, and you can download it from the website as well. So last time we briefly introduced least square setup a little bit, but we were in a rush, so let's start over again this time. So the goal of this lecture is trying to do system identification. Okay? So the previous lecture, lecture note 2, is how to derive system model, state space model from first principle, okay, from physics, and then do the things from analyticals. Now, this lecture, we're trying to see how do we build or develop system models from data. You can measure the input of your circuit, measure the, you can apply some current to your circuit, then you measure the voltage, whatever the input output relation is. You take those measurements. You want to understand what's the RC circuit parameter. That's possible, right? So that's the development of the model based on data, okay? The way we're going to use is called least squares, okay? And because least square is so important, and we're going to cover a little bit more than what we need. So last time we mentioned least square can be applied. It's a key for many fields, right? Control robotics, signal processing, machine learning. It's actually, I think that's, least square shouldn't get those credits. It's actually optimization is the foundation for all of these and also more beyond. All the things you're doing now, nowadays, no matter what you're learning, robotics or machine learning, entire machine learning is trying to do optimization, okay? Your deep network, your training is to do what? Is find the best optimal solution to minimize the loss, okay? The key is solving optimization. That's the key for almost everything. And least square is a particular simple optimization problem. We have analytical solutions when it's a linear least square. So that's why people think it's important, because that's one of the few cases you have an analytical solution, so you can somehow get a deeper understanding and extend your understanding to something more advanced. Okay, so we have 2 more minutes. Let me say a few more words about the setup of this square problem. Last time I don't think I make it clear. So what the purpose, at least in the context of least work and other least square problem, you are trying to estimate something hidden. This is a hidden variable. Means you cannot see. It's hiding from you, it's hidden from you, okay? But this is something you can measure. Using something you can measure to estimate something you cannot directly measure is estimation. Okay, so I can give you a quick example. Suppose you have a card with a mass. Okay, you don't know the mass. Okay, you don't know the M, but you can take a measurement. For example, you can take a measurement. This is the force you applied. Maybe this is the position. This is xt. Suppose my data would be, I don't have a scale. I cannot measure how heavy the card is, suppose, okay? That's the hidden variable to me. But I can measure the force applied, in this case, maybe Ft1. And at any given time, I can also measure the position of the card. Suppose that's only 2 measurements I can get. So Ft2, another time I sample that again. Okay, I can have a table of data. Okay, my question would be, how do we use this data to estimate the mass of the card? In this particular setup, all this data together, this is my y. I put them all together and become my y, and also somehow the relation is in this guy, okay? And And also, this is my y and g. You will see how it works later. And in this case, theta is m. Okay, you're trying to estimate m. You cannot directly measure it directly. You can measure it from, you can estimate it from your other measurement. Okay. In order for you to be able to use your information, which is y and g, to estimate theta, you have to know how they are related. If they're not related at all, you don't know how to use one to estimate the other, right? You have to know the relationship, and the relationship is given by the measurement equation, okay? That's your knowledge or prior knowledge you want to use to estimate, okay? And in this case, the theta has to be bigger than 0, right? Because it's a math. So the theta has to take values within some constraint set, which we call this capital theta here. Okay, so the entire goal is that how do we set up optimization problem for which we can find the best estimate of theta given the data I listed here. Okay, you will see that later in this class, even today, okay? All right, let's take a break. Okay, let's continue our discussion on least squares. Okay, so let's, this is the basic setup of the least square problem. Let's look at the example. Let me jump over a few slides. Let's directly look at this first example so that you can have a concrete sense of what's going on. This kind of problem, I think, is easy for you to understand. Suppose I have a few points, right? So this is my x coordinate. This is my y. Okay? I have at different x locations, I measure y. I have a few data points here. Okay? Now I'm going to ask you, can you find the biased line model approximating this data? Line means y is a linear function of x, right? If that's a line, so basic structure line is that, okay? Roughly speaking, you wouldn't have exactly, because your measurement noise, your modeling uncertainty, you may not fit perfectly. So you can see these guys are not on the same, on any lines, right? All you can do is find the best approximations. Okay, in this case, let's see how we can go back to the basic setup. So then I'm going to ask you, if I want you to estimate a line, so what's the theta in this case? What's the parameter you need to estimate? Can you not, excuse me? I hope you don't discuss after class starts, okay? Especially we're also recording, sometimes we upload this online, so I don't want you to, okay. Anyway, so if I want you to estimate the parameter of a line, what do you think the parameter is? It's x, alpha, y, beta. There's only 4 variables here. Alpha and beta. What about x and y? These are input-output relation variables, okay? So the parameter is alpha and beta. So let's say alpha, theta is alpha and beta. We like vector, everything we want to put into vector, right? That's our theta. Okay, if we want to write our relations between input output, so the measurement, I have how many points, data points? 1, 2, 3, 4, 5, right? Y1 should be approximately what? Alpha times x1 plus beta, okay? Y2 is alpha x2 beta, dot, dot, dot. Y5 should be alpha x5 beta. I'm just blindly writing down the relation at different time. If I assume it's a line, then the data x1, y1, x2, y2 should satisfy simultaneously these 5 equations. Of course, they don't. So there's always some noise, I assume. I don't assume a perfect match, but at least as close to my assumption as possible. Does that make sense to you? Okay. Now I would say this is, if I want to write in the matrix form, and you should always think about things in the vector matrix form. So it's almost like this is y vector is in R5 in this case, right? But I can write it the right-hand side inside my bracket. If you don't care about v, these are a linear function of alpha and beta. So I can write it like the following. That's my alpha and the beta plus v vector. Okay? Can you tell me the first row of matrix? This is x1, sorry. This is x1 and 1. This is x2 and 1. All right? This is x5 and 1. Okay, and then so basically I have find this is my theta, right? I call this h. Okay, so roughly I find a relation to somehow, okay, h theta plus v. That's my relation. What are the knowns? I know this guy. These two are known. This guy is to be estimated. Make sense? So I have y equal to h is known, okay, times theta is unknown, plus some possibility, some noise, because I don't expect they are exactly linear relation. And I want you to estimate what's the theta, okay? So in this case, if you would like to go further, this is my g of theta function. In this case, it's very simple. G of theta is just h times theta. In general, it's a function of theta, can be arbitrary. Okay. H times theta is our g of theta. It's our model. What h of theta trying to say? If you tell me this is the parameter, g of theta tells you, okay, I expect to see the measurement of g of theta, which I can say this is y hat. Okay, based on my model assumption, I hope I will see y hat like what. But in reality, you will see some other measurement y. The difference between these two will be the discrepancy. You want to minimize them as much as you can. So g of theta in this case will be telling you, if you give me this x1, 1, if it is perfectly line, okay, if I give you some parameter, then you tell them what is the output should be, okay? So I hope this explains the setup of the square problems. Okay, you have measurement. You can see that the data, x and y, they somehow appear in y and h. Okay, so the data actually come into not only y, but also the g function as well. Okay, so that's enough. Now let's go back. Now I hope you find the formulas incomprehensible now, but let's say our formulation, okay? So now the question is that, okay, you get data, you get this relationship, how do we estimate theta? The first question you will ask is, what is the good theta versus bad theta? I don't know where I should, let's see. If you don't mind, I will erase this, then I have more space. It's not useful. Let's say I have a data point just like before. I have these 3 data points. This is y1, y2, y3. That's my 3 data points. There's some x as well. I don't write everything down. So then I have my, let's see, this is my G. This is my G1 of theta 1, G2, sorry. The circle is G, okay? G2 of theta 1, and this is G3 of theta 1. So I plug in the parameter, theta 1, then my model tells me, okay, I expect to see these G's, okay? G will be my predicted output, okay? Then you see, oh, it's not perfect. So circle is not completely aligned with the cross. So it's not, there will be some error, all right? This is one theta 1. Maybe I have another theta 1. This is G2. This is maybe another one, okay? This may be my G1 theta 2, G2 theta 2, G3 theta 2. I'm not sure whether you understand my notation, okay? I changed theta 1 to theta 2. I still have 3 expected, model expected output of. But this guy seems to deviate from the cross or even further. Depending on you, okay? Depending on criteria. So which one is better? Theta 1 vs theta 2. Which one is better? Theta 1 is better. Why? So theta 1, according to theta 1, G of theta, if you think about this vector, minus y, the vector, okay, y1, y2, y3, the norm seems to be smaller, let's just less than G of theta 2 minus y. Can you see the vector notation? This is very, just based on my drawing here is definitely the case, right? Theta 2 deviate more from your observation than theta 1. Okay? That's intuitive. That's, I mean, of course, I can design a cost criteria. Maybe my purpose is deviate from the data as much as I can. So in that case, theta 2 will be better. Okay? That's up to you. The cost criteria is up to you. But if we agree upon the cost criteria, then we should find the best solution. So our goal now is trying to find the theta which can minimize y minus g of theta. Okay? Does that make sense to you? So there's so many theta I can choose from. I want to pick one, minimize the apparent, it's called apparent error. So it's how much the model predict output versus the model output, okay? So we changed the estimation problem to an optimization problem. So now our main purpose is solve this optimization problem, right? Do you know how to solve this optimization problem? Minimize something. Okay. Yes, gradient or take derivative is one way to, or it's a key element to solve optimization problem. But that's not the whole story. Okay. So now our goal, I hope you find now. Okay, our goal are shifted to solving the optimization problem. Okay, and no matter what happened, this is called least square problem. But because of g of theta may be linear or nonlinear. Okay. So in this case, G is h theta, just like the line fitting problem, that's a linear least square problem. If G is nonlinear, that's nonlinear least square problem. But these are the same principle. They follow the same principle. You want to find theta agrees the most with your data. Let me repeat. You want to find theta agrees the most with your data. How do we define most? Agree is the norm, the squared norm. So that's why it's called least squared, okay? I hope that's enough. So now let's shift to solving optimization problem. You all learn from your, hopefully, calculus. At least you know derivative, right? Hopefully that's fine. We start from derivative. Let's recall, okay? Let's say suppose you're more familiar with a scalar kind of single variable functions. If I want to find the optimizer of j of theta, what we should do. For example, let's say we have a first dimension. Let's say theta is in R, okay? How do we optimize it? Yuntian said it should take derivative and make it to 0. But let's find a stationary point or critical point that can be possible a candidate of optimizers, right? If you function like this guy and this guy are possibly maximum, minimum, right? Why? Why gradient equal to 0 tells you that's possibly a optimizer. Because by definition, optimizer means what? You cannot find better ones, okay? Local optimizer means locally, so just very close. So this guy's local, okay? Very close, because further away there may be other things. So we cannot get those information from gradient or derivative. We can only get information regarding the function shape locally around the point we take gradient. And means locally I cannot find any better solution. Okay, so roughly speaking, j of theta will be j of theta 0. That's my Taylor expansion plus partial j partial theta evaluated j0 times theta minus theta 0. Sorry, not z0, theta 0. Plus high order terms. Some people ask me what is hot means. High order terms like this is a little o of theta minus theta. Little o, you know what the little o is, right? As theta go to theta 0, this guy go to 0 faster than the previous terms, okay? High order terms. That's my shorthand notation. Okay, based on Taylor expansion, first order, okay? Let's say if theta 0, then partial j, partial theta, evaluated theta has to be 0. That's Yuntian's theorem, right? Has to 0, but because let's explain, let's prove. Because if not, okay, if not, it's two cases, either bigger than 0 or smaller than 0. That's only two cases, non-zero, right? So if let's say if 1, partial j, partial theta 0, bigger than 0, I would say then theta 0 cannot be an optimizer. Why? We can always find a better solution now. The only way to contradict that is that you should find a better choice. What's the better choice? We can choose, let's call the theta hat equal to theta 0 minus epsilon, a little bit to the left. Okay, because this guy is bigger than 0, that slope is positive. So you move a little bit to the left, you further decrease the value of the function. Okay, so then I can say in this case, theta hat will be less than theta 0. Why? This guy is bigger than 0. I move theta hat less than this, there will be small, this is a negative number. So z theta 0 negative number equals to j of theta hat. So j of theta hat is smaller than j theta 0. Okay. If this similarly, right? So if this bigger than 0, smaller than 0, we can choose this guy plus epsilon. I can still find this guy. The same conclusion, right? If that derivative is smaller than 0, then I need to move to the right of theta 0, so I can still have a better solution. So the only case that's possible, if the system is, if the function is continuous, is make that equal to 0. So 0 is very important but it's only locally important, okay? You may ask why we care about the scalar case. We already know all of this. Because all we build upon, all the multivariable calculus build upon single variable calculus. If you can design, just like our Z transform, we define in terms of scalar, then you find that, okay, vector is fine. The same definition works for vector case. So if you know scalar case, there's not too much, at least theoretically, it's almost done. But conceptually, when you see a bunch of vectors, make you more confused. That's possible. Okay, that's a first order scalar case. But then if we have a multivariate function, okay, that's different. The derivative will become a Jacobian. Okay, we already learned this for the linearization part. Did we? Okay, so this guy is, by definition, the derivative of f, if f is a mapping from Rn to Rm, is a function, right? Partial f, partial x, ij is a function. The ith row jth column equal to partial fi divided partial by partial xj. Because f is a vector, x is also a vector. And this guy tells what? Tells the slope of the ith component of f changes as we change xj component. You see what I mean? The derivative thing, it only tells you if you move x a little bit around ith coordinate, how the fj's coordinate changes. The slope is how fast they will change, okay? You can think about vector as just putting together the scalar definitions, okay? So the question I want to ask you is, let me do that through example. Suppose my f is from R2 to R3, okay? So then I will have, if I write like this, I hope you have I don't want to repeat this in the future, but I want to write it now, okay? So that will be f1, x1, x2, f2, x1, x2, and f3, x1, x2. Do you get that? In the future, I will not write this. I will just write fx, but in your mind, you should know x is R3, yes, R2, and my y is a vector in R3. That's how we arrange them. I think if I write like this, all of you can see what's going on. If I write like this, then you may feel a little bit uncomfortable. But hopefully you can establish this relation. Okay, so infinitesimal perturbation of x will cause f to change, but both are in the vector space, right? So now I'm going to ask you, what is df? df is what? Infinitesimal change in f in R3. Okay? df, in the scalar case, df is what? F prime dx. Is that true? The derivative of x, f, if it's just one variable, one output, right? In the scalar case, it's nothing but partial f, partial x times dx. If I write like this in the future, you shouldn't think just scalar case. You should think in this way because you know the definition of this guy, right? This is what? Partial f1, partial x1, partial f1, partial x2. And I don't want, this is three of them, right? Partial f2, partial x1, partial f3, partial x1. Sorry for I think you know what I mean, okay, hopefully. So it's a 3x2 matrix times dx. What is dx? dx1, dx2. So I asked you before. So for example, I pick this element. What does this mean? The slope f2 changes with respect to x1 changes, right? If you multiply them out, this guy change will be multiplied by this factor, right? So a positive change, a positive slope will cause a positive increase in F2, but only in the F2 coordinate, not in other coordinate. Okay, now I'm going to ask you or telling you, if nothing can be changed, then I need this partial F, partial X to be 0. Because it's non-zero, I can always perturb nearby that. I can set this guy 0. I only perturb one of them. Okay, I can change or alter the value of the function f. Okay, in this case, a little bit strange. F is a vector value. It's not some optimization cost function. Cost function has to be a scalar, by the way, right? It's good or bad. It's not like a multi. Okay, so but that's a general discussion of the gradient. Or sorry, this is not gradient. This is a partial derivative. Okay, so for optimization, we care more about the special case of the partial derivative, which is called gradient. Okay, so gradient is a function from Rn to R. This guy from Rn to Rm. F is multidimensional. Okay, so if it's from Rn to R, it's just a scalar. That tells you good or bad. Okay, the cost function. Then you must have learned this, right? The gradient, typically I write like this. Have you seen this? Nebula, how the upside triangle down, okay, triangle upside down. Partial, this is called gradient of f. Depending on the book you read, depending on where you look for it, most of people use a column vector to represent the gradient. Some people use row vector. I use row vector before even, okay? It doesn't matter as long as you know your convention. But now let's do it similar to most of the textbook. Will be partial f, partial x1, partial f, partial x2, all the way to partial f, partial xn. Okay? Is this okay? So that's, did you learn gradient, by the way? You learned, right? So that's the definition of gradient. Then in this case, and so notation convention, the gradient is the partial derivative transpose. Okay, I'm not sure whether that's, but some people use this to denote gradient as well. So, but let's say that in this class, gradient is just partial derivative transpose. Because if you look at this definition, the Jacobian definition we have been using, then in this case it will be partial f, partial x1, because f is scalar, right? So only have f1, there's no f2. So f1, x1, x1, x2, f1, x3, all the way to fn. So it's a row vector. Now the gradient I'm defining is a column vector. So typically I would say this is the case. Okay, in this case, you will see the notation like a df equal to the gradient inner product weights dx. Okay. Transport time dx is inner product. Okay, that's almost like this. Okay, so that's the gradient. And for least square problem, let's say for LS problem, okay, we have a J from R, what is it? Rn or Rm, I forgot. Rn to R, right? That's our J cost function, J of theta, right? Theta is Rn. So our optimality condition should be necessary optimality condition is not sufficient, but is gradient of J evaluate theta equal to 0. Okay, let me say gradient of J theta star equal to 0. Okay, if gradient is non-zero, what will happen? At least one of these guys are non-zero, right? Maybe some of them are 0, but some are non-zero. But let's say this guy is non-zero. Let's pick one. This guy is non-zero. what you can do. I can find a delta x equal to 0. For these guys, depending on this is maybe positive. Let's say positive. What is it? If it is positive, I need to move to the left. So then this is theta minus epsilon 0. Okay. If I take inner product, I pick this guy out, then I can make the function cost or the value of the function go smaller, so it won't be a optimeasure. So we almost prove it. Okay, so we require this gradient, the vector gradient, to be 0. The reason we do it is that it's the same principle as we applied here. Okay. There's another terminology I don't want to spend too much time, at least today, for talking about this. So directional derivative, I think most of you have learned this, right? So directional derivative, let me emphasize, although I'm not going to use that a whole lot in this class, directional derivative is the key for understanding a majority of optimization problems. Okay? Gradient is nothing but the summation of gradient directional derivative. Even for optimization or trajectory optimization in functional space, you still directional derivative is the key. Okay, I don't want to repeat that. If you want, you can find directional derivative definitions. This is, by the way, is nothing but gradient inner product with the direction you are moving. Okay, so along certain direction, everything becomes a scalar derivative. Okay, so direction derivative is it's along that direction you fix a line and move along that line. That's become a scalar function. If I have a multivariate function, I define a line, I move around that line, then that become a piece, a slice of that function. Then I can use whatever scalar world result to analyze it. Okay, let's not worry about that. All I want you to know is gradient equal to 0 gives you at least a candidate for optimeasure. Okay. So now the question is that how do we find the partial derivative and the gradient? Okay. The first one is, suppose, let me be simple. Okay. So this guy is let me use some example. So X is Rn, okay? A is Rm by n. Right? So Fx will be in Rm. True? So what is a partial F? Huh? How do you find it? You are trying to remember what formula you have learned before? What's the formula for this? By definition, you should be able to calculate it, okay? Everything from definition. If there's something I wanted to remember, I will tell you up front. If anything hard, my answer is always from definition. It's not my answer, that's the way it should be taught, but somehow you don't. By definition, is partial F1, partial X1, partial F2, partial X2, partial F1, partial X2, ... right? I don't want to write all of them down. But if you look at particular example, let's for example, F1 of X. What is it? The first row of A times X is, let's say A equal to A11, A12. Let's use those shorthand notation. So the first row of F is what? Is the first row of A times X. So it will be A11, X1, A12, X2, all the way to A1, N, Xn. So we will know partial F1, partial X1 equal to Now you know what it is, right? What is it? X is a variable, other things are constant. So this is A11, right? What about partial F1, partial X2, A12? By definition, and your knowledge about scalar derivative, everything will be defined. You just need to take your steps to go through the definitions. So then I can find out this is nothing but A. If you arrange its term, is nothing but A. So it's similar to the scalar case. But I don't want you to memorize it. But now you can memorize it. But you know how it comes, where it comes from. Okay. Now I have another question. Okay, so that's even more useful for us. It's fx is x transpose A times x. So in Rn, A is Rn by n. In order for this multiplication to make sense, A has to be squared. So what is f now? From Rn to R. That true? Because this guy is a column vector, and x transpose is a row vector. Okay, this is a scalar. So what is f partial? Let's directly say, in this case, I can say gradient, okay? What is gradient? Partial f1, there's no f1, it's just f partial f, partial x1, all the way to partial f, partial xn. Okay, that's my gradient. Do you know what it is? We need some kind of a little bit of work. So if you, let's call it a, so this guy equal to, okay, let me draw a few blocks. Summation I, summation j, aij, xi, xj. That's the summations, okay? This is quadratic forms, okay? If you think about this x1 to x2 squared, something like that, up to second order of x. Okay, if that's the case, if I want you to say what is partial f, partial x, k is arbitrary, 1 to n, okay? That will be, if you arrange all these terms, so you think about this sum of all the square terms, okay? Some of them relate to k, some of them don't. Are you with me? Some of the terms depend on xk, some of the terms don't depend on xk, okay? There are only 3 cases. Okay, partial xk. What is the first one? So I not equal to k and j not equal to k. Aij, xi, xj. So this guy, if you take derivative, will be 0. Okay, it doesn't depend on k. And there's also another case is that only I not equal to k, but j equal to k. But j equal to k, I can fix j now. Okay, it's just one term. So j could not equal to this. So I, this is a, small a, this is a, I, k. Okay, j is k, fixed. So this is xi, xj become k. Okay, and plus summation j not equal to k, but I equal to k, so it will be akj, xk, xj. Okay, and plus both of them are equal to k. So I don't think that's only one term. So that will be akk times xk squared. You should be able to do this much better than I do, so I skip some details. So those are nothing. I want to emphasize conceptual hard part to explain. So those calculations, I hope you can take care of it. So eventually, believe or not, I will skip maybe 1 or 2 steps only, or not too many. Take derivative eventually will become partial f partial xk will be a k dot dot times x vector plus a transpose. How to say it? Let me write it more carefully. Sorry. So let's say j, the I from 1 to n, a I k x I. That's the first summation. That's left. Second summation is summation j from 1 to kn, a kj xj. Okay, so that's the case element of the gradient is like this. This thing about this is ith row of a matrix. This is the case row. Sorry, case hold on. Case column of J A. This is the case row of A. Okay, so eventually, believe or not, partial f partial this guy gradient equal to A times x plus A transpose times x. If you put all the this is only the case element. If you put all together, you have ith row and ith column both times x, so it becomes A and A transpose times x. Okay, that's the case. If A is symmetric, what we got is symmetric means what? A equal to A transpose. That's the definition of symmetric. So we have derivative of this is 2ax. In the scalar case, derivative of x squared equal to 2 times x, right? Here in the vector form, gradient of f is 2 times a times x. It's similar, but slightly different, okay? There's other more involved case. For example, this is a this is involved third order terms, and you can do this by definition, okay? Verify yourself the result, okay? I don't want to go through this. This will be some just pure arithmetic steps. Any questions? Anyway, I just show you the key steps to derive the partial derivative of fx equal to x transpose ax. I hope that's good enough for you to derive it further, okay? I think I just missed a few steps, but the key ideas are already here. All the way, everything goes back to the definition. If you understand definition, you are good at the calculations, you can do all of this. If you don't, you can still survive by remember. This is your result, okay? With this result, we are ready to derive the least square solution. I think many of you have learned this from multiple classes, right? You should know the solution better than I do, right? How many classes have taught? I mean, linear algebra. In linear algebra, you will learn this, right? Least square. If you took machine learning, you definitely have learned this. I'm not sure other class, maybe in this class, okay? Derivation of linear least square solution. Key word here is linear, okay? There's no solution or no analytical solution for nonlinear least square. Let's recall our definition. So what we want to do is minimize over theta, and we don't have a constraint in this case. A cost function, let's call it least square cost function. That's fine, that's J, okay? The J in this case is minimized over theta, is y minus h theta. Okay? G of theta is h theta in this case. And we have seen the example. For the line fitting example, this is exactly the case. There's a square here, d squared. How do we do it? Take gradient. What are the best theta? At least theta should satisfy gradient of theta equal to 0. That's the requirement. Otherwise, we can always find better solution. That's how we discussed so far. And so J is from Rn to R, right? So let's write it out. J of theta equal to y minus h theta squared. A vector squared, norm squared is the inner product. So I will say y minus a theta transpose times y minus a theta. I think everyone can follow this part. Of course, everyone can follow all the other steps as well. The next step is everyone likes. It's pure multiplication without thinking, right? So it's just multiply, okay? So you get this y transpose y. This guy transpose is theta transpose h transpose times y, okay? And then we do the other term is minus y transpose h theta and plus theta transpose h theta. Are you with me? I'm surprised nobody sleep. Okay, that's it's afternoon. Okay, and this is math. Okay, now I'm going to ask you if you still haven't fallen asleep. What do you think these two guys are? What's the relation of these two guys? These two guys looks different. They are transpose of each other. If you take transpose of one, you got the other. Okay, so I'm going to note. I'm going to claim theta transpose h transpose y equal to y transpose h transpose. Y transpose h theta y. What vector is transpose equal to itself? Scalar, right? It's a scalar because it is a scalar. Of course, this is a scalar. If you take transpose, it's the same. Okay, so this guy is almost like it's similar to. I'm gonna give you an example. You like numbers? I think that would be good. 3, 4 times 1, 5 equal to 1, 5 times 3, 2, 4. Okay. It's the same. You can immediately see these two are the same, but I want to also immediately see these two are the same as well. Okay. Now, given that they are the same, I can pick an arbitrary one, depending on how my notation, which one is can simplify my notation. I will say it is equal to y, let's regroup it. So this will be theta transpose h theta, the second order term in terms of theta, minus 2 times y transpose h theta plus y transpose y. Okay, that's the somehow, why cannot erase it? This is the same as we defined before. I'm just writing out all the terms, okay? Now I can take derivative. I say gradient of theta, j of theta equal to what? The first term, gradient with respect to what? Theta, okay? Theta now is my x, is a variable I want to take derivative over. This is X transpose AX. And this A is symmetric, right? Can you see it? If you take transpose, somehow you get the same thing. So you can prove any function of this, any matrix of this form, no matter what H is, it is a symmetric matrix. In fact, that's how you generate the symmetric matrix in MATLAB or Python. If you want to say, I want to generate random symmetric matrix, but I want to make sure it's symmetric, you just randomly generate a matrix H, you transpose, then you got a random symmetric matrix. Okay, that's how it generates symmetric matrix. Okay, this symmetric, so I can get 2A, which is H transpose H theta, minus this guy. This is a 2AX, all right? And you remember this guy? Equal to A, right? Partial derivative equal to A, but the gradient is the transpose of partial derivatives. So I have this A transpose will be my gradient. So that will be 2H transpose Y. You see what I mean? Partial derivative is transpose gradient in this class, okay? Okay, so I need to make sure this guy is 0. Plus 0, this guy doesn't depend, so equal to 0. So then I have what? H transpose H theta equal to H transpose of Y. So that's the so-called normal equation for these square problems. In other words, the best least square estimate should satisfy this solution. This equation is called normal equation. Of course, you want to invert it, right? So this square solution you have seen before will be H transpose H inverse H transpose Y. Okay, that will be the least square solution. But of course, we are a little bit more advanced than that. So we don't allow you arbitrarily take inverse. You have to discuss when you can take inverse, so on and so forth. Okay, so this is our key step here. Okay, we'll discuss different cases for least square and what's the geometric meaning. And then we will see a few examples how to use that to do system identification next time. Okay, let's get started with the continue our discussion on the least square problem. I think that's one of the most important concepts for many fields in engineering. And the last time we start by formulating the least square problem. I hope you still remember the basic setup for least square problem. So you have something hidden that you want to estimate, but you cannot directly measure. Now, why is something you can directly measure? And their relation G is known. Okay, it's model. You have to have some model assumption, and the theta is some parameter of your model. The model structure, in the sense that how the model depends on theta, is known ahead of time. Okay, so G is something you know, and theta is something you want to estimate. And the goal is that we want to estimate, or we want to find theta that minimize the discrepancy between the measurement and your model predicted output. Okay? You model, if you give me a theta, the model will say, okay, if this is a theta, then the output should be G of theta. But in reality, you see something about, it's different, it's Y. And all your purpose is try to find the best theta to explain the data Y, okay? So that's why the whole problem becomes, or reduces to, a optimization problem. Okay, the optimization has a particular form, squared error, and so that's called least square problem. And we focus on primarily the case of linear least square, where G is a linear function of theta. you're trying to fit your data with a linear mapping, okay? Of course, that may not be possible oftentimes, but you want to find the best among all the possible thetas out there. So, and last time we start talking about or review how to do the optimization problem, setting gradient or derivative equal to 0, right? If it's non-zero, you can always perturb nearby that particular point so that you can have a better solution. That's the key principle. And I think the last time after class, a lot of people asked me a few questions, and one of them was confused by this, okay? So that's here, the Jacobian, okay, partial f, partial x, according to its, I think, the most common definition, is defined by its partial fi divided partial xj, the ith row and jth column. That somehow is the transpose of gradient. So whenever we use gradient, we need to take transpose of that. And that's, for this particular case, what we're deriving here is Jacobian, okay, partial f, partial x, okay? And if f is mapping from Rn to R, in this case, you wouldn't be able to have an A matrix, you will have a vector, right? So fx will be A transpose x, that's a vector, so that become inner product. Then, in this case, the partial f, partial x is A transpose, but the gradient of fx is A. You see what I mean? Gradient is transpose of Jacobian. We introduced Jacobian last lecture for the state space model as well when we do linearization. But that's in optimization problems, we often have a scalar valued function. In that case, the the gradient is the transpose of Jacobian. So that's why when we derive this optimality condition, where is it? Here, right? This is something times theta, but this something is a row vector. If you can see that, that's a row vector, right? That's almost like this A transpose, okay? And when you take Jacobian, will be this guy transpose, will be H transpose times Y. That's where this term comes from. Then we obtain, if it is equal to 0, we obtain this optimality condition, okay? Which we call normal equation. It doesn't matter what we call it, it's just when you set gradient equal to 0, that's what you get, okay? Any questions up to this point? Okay, now let's talk about solutions, all right? So what does this equation tell us? Yuntian, what does this equation tell us?
This equation tells us the H transpose Y is the linear combination of
okay. Okay, that's great. Okay, you start thinking that way. Okay. Well, that's not what I'm asking, by the way. So, but that's fine. But that's good. Try. What I was saying is that the optimal theta has to satisfy this. Okay. Whatever theta that minimizes the least square, the squared cos j of theta have to satisfy this condition. This is somehow a necessary condition. Okay. Now we need to solve this one and to find the optimal one or the candidates for the optimal ones. In this case, it will be the optimal. So let's discuss when the solution, what's the solution, and that's why we reviewed a lot of linear algebra, right? Some people ask me, so it has been a month almost since we started this class. We haven't talked anything about control yet. And we spent quite some time reviewing linear algebra. And frankly speaking, I think you have learned all the hard part of this class. The rest is just put those linear algebra concept into the control context. You see, what I'm discussing here is nothing but linear algebra. Now we are going to discuss when this guy has solution. I think we talked about them for linear equations for the review, right? So let's recall recall, let's say H belongs to R, based on our notation, M by N. We have n-dimensional parameter we want to estimate. Everything is a vector in this class, okay? We have n-dimensional parameter we want to estimate, and M measurement equations, okay? And we assume, in general, for simplicity, let's assume we have more measurement than the number of unknowns, okay? This is an over-determined problem, okay? It's an over-determined problem. That's where we need least square. But the discussion also works, most of them works for M less than N, okay? So the normal equation is the following, okay? Let's write it here again. Normal equation is H transpose H theta equal to H transpose Y. Think about this as AX equal to B, right? The first case I want to discuss is that maybe I will go to tell you a fact, all right? If H is full rank, okay, let's say, because I assume M bigger than N, the rank of H equal to N, suppose. Okay, it's full rank. We reviewed full rank, right? And that's almost equivalent to say H transpose H, which is a N by N matrix, okay? That's equivalent to say this guy, let me pull it out. This is N by N matrix. It's non-singular. What is non-singular? It's full rank for square matrix, it's non-singular, okay? All the columns, all the rows are linearly independent. If they square, that would be non-singular. Okay? If it's not a square, it's a rectangle matrix, more rows or more columns than the other dimension, then you have full rank. You can only say it's a full rank, okay? So it's non-singular. Do you know why? So if H is full rank, so full column rank, then this is non-singular. And it is actually equivalent. I think you can do it. So I will say this guy, my favorite 3 words. Verify yourself, or I will give some notes later on. Okay, I don't want to derive them, but it's a I wouldn't say simple, but it's a fact for this basic property for linear algebra. Okay, so whenever this is non-singular, you have A times theta. That becomes easy, right? So in this case, theta least square best estimate will be, you invert. The inverse exists, right? Non-singular inverse exists. So that will be inverse times H transpose Y. If the columns are, so full rank here, it's just the columns are linearly independent, then H transpose H will become a N by N non-singular matrix. You can invert it to find the solution, okay? Where is it? Okay. Let's see. Another case, which is, let's say, if H is not full rank. Suppose it's not full rank, what will happen? Because if and only if, right? So H transpose H is singular. It's a square matrix, it's singular. Can you invert it? No, right? So then my question is that, what can you say about the solution of the least square problem in this case? Do they have a solution? So let me say, okay, it has 0 solution, there's no solution. There could be 1 solution, there could be infinite many solutions. Which one? Yuntian said it's always possible. Okay, let's see. It's singular. You may like examples. Okay, singular means columns are linearly dependent, right? So let's say H transpose H equal to 1, 2, 2, 4. Is this singular?
Yeah.
The second column depends on the first column. It's a linear combination of. And I give another. So suppose in this case, my data times H equal to 3, 6. Okay? In this case, how many solutions I have? Huh? How many solutions? Theta least square would be, let's see, could be anything, right? So could be 3, 3, 0. That's one solution, right? I mean, this guy is your B matrix. This guy needs to be a linear combination of columns of H transpose H. That's what we've been reviewing. So if you think about it, if theta is, right, this guy is theta, right? Theta is 3, it's 3 times the first column, it gives you at least 3, 6, then the rest column doesn't need to exist, right? What's the null space of, let's review again. What's the null space of this guy? After homework? It's just one negative, yeah, that's right, 2, -1, right? That's fine, right? 2, -1, that gives you a 0, so that's a basis vector for the null space, and also because of conservation of dimensionality, you know rank is 1, so null space dimension is 1, so that's all. The null space is span of this guy, right? This is the span of 2, -1. Okay? So this is one solution and plus all the possible null space solutions. Let's say alpha times this will be all your solutions, infinitely many, and the solution forms a line in this case. Okay, it's a line. This is a line form. Okay, and the same example, now let's say second example 2, H transpose H, it's still 1, 2, 2, 4. This guy equal to 1 and 1. Is there a solution? Do you know where to think of? This guy is your B, right? B equal to H transpose H times theta, and it's something theta you need to determine has to be in a column space of H transpose H, right? So this guy has to be in the column space of H transpose H in order for the solution to exist. Is this in the column space? Any questions? So the span of H transpose H, that's the column space. The span, let's directly say column space. The column space of H transpose H is just span of 1 and 2. Okay, it's one dimensional. So this guy will never be, this guy is never possible to be in the span, so there's no solution. Okay, both are possible. So if the data somehow agrees with this column space of H, then there's infinite many solutions. If it's not, there's no solution. But it's no possible to have just one solution, okay? I give you 3 choices, 2 are correct. 2 are possible, 1 is impossible. If you have solution, let's say ax equal to b, if a is singular, if there is a solution, there must be infinite many because there's a non-trivial null space. Null space give you the solution dimension. Okay. All right. Let's. That's a quick summary of what. Yes.
那个 H transpose H， 那是应该是属于一个 H transpose， 就是 H T 的那个空间里的。那个 H T Y， 那应该也是属于同一个空间里的。就一个 column space H T 的一个 column space。所以说你那个红色标出来的这样子一个存在的。就是说，我觉得两组的 STH 和 STY 这两组应该是属于同一个空间里。就是都是在 column space of HT。
我想想看啊，有可能。你说这种情况不存在，就这种情况，我是说，如果有这种情况，它不存在，它就有 no solution。你说这种情况本身就不存在。我要想一想。不一定吧，我看看啊。H， 你要知道 H， 我看看啊。Anyway， 如果我们有这种情况哈，这个是 no solution， 是不是一定会有这种情况？你说这种情况乘出来不一定存在，这是有可能的啊。我回去看看哈。好。但这句话没有问题啊，如果是这种情况就会，但这种情况有可能时间用不上。OK， so let's talk about geometric interpretation of the least square problems. Okay, for any theta, okay, belong to Rn. Let's think about this, right? So, Yuntian, what do you think this now your solution? How do you think about H times theta?
It is the linear combination of the columns of H.
Excellent. Okay. Whenever you see matrix vector multiplication, think about it as linear combination of columns of A. Okay? It's a linear combination of columns of H. Okay, that's this guy. H times theta. Why we discuss H times theta? Because we're thinking about our cost is y minus H times theta squared. Okay, that's our cost. We want to find theta so that H times theta stay as close as possible to y. Think about in the space. This is Rm space. Y lies in Rm space, and H times theta is also in the Rm space, and we want to make sure these two vectors as close as possible. Okay. So if y, let's say, belongs to the column space of H, what do you think? We are trying to minimize y minus H theta, right? If y belongs to the column space of H, what do you think this minimization should return? The cost should be 0, right? You can always find theta such that y equal to H times theta, right? So we can find theta hat such that y equal to H theta hat. Why? There's no y. It's just by definition, this is just agrees, okay? Don't memorize any formula. If you say it like what I said, y belongs to the column space of H means y is a linear combination of columns of H, right? So y can be written as H times theta for some theta. That theta is the linear combination coefficient for y. Okay, so that's, and then in this case, J of theta hat should be 0. If I plug in this theta hat, of course, y equal to H theta hat, then that will be 0, okay? But in this case, I want you to verify yourself. There's a few things you need to verify after class, is that if y belong to column space of H, then J of least square solution is 0. Okay, we have, I mean, our solution have to agree with our intuition. This guy, so based on our general discussion, we think the cost should be 0. Okay, but our solution is given by a formula. You need to plug in that formula to see whether that agrees with your intuition. Otherwise, you didn't solve the problem correctly. So this one is what? H transpose H inverse, let's say that, okay? Y. So IE, oh, okay. IE, what we have is y minus H theta, right? H times the least square theta is H transpose H inverse H transpose Y should equal to 0, okay? I'm not sure whether you can verify that. This is actually 0. Square, okay? Square or not is fine. So that's almost a trivial case. You just play with it, you will find it out. I want you to think. I don't want to tell you everything, but this guy you can think. Now the non-trivial case is oftentimes, okay, you don't have a 0 least square error, you have non-zero error. That means y is outside the column space of H. Okay, so y does not fall into the column space of H, so there's no exact solution. Okay, there's no exact solution, so we have to find the solution with minimum distance. Okay, so by changing theta, you are changing this H theta as a vector, right? But you know this vector will never be agreed with y, and you want to find the minimum distance one. Okay, find the minimum distance solution. Geometrically, that can help us, okay? The geometric stuff that we introduced before. Let's schedule through that geometrically. Let's, for example, okay, I want to talk in terms of example H, it's 2 column, H1, H2. Okay, so what I have now is, this is our column space of H. Can you tell me what it is? This plane is a column space of H. If I say that, what do you think? Every vector on this space is a linear combination of columns of H. Okay. Okay. So we also know, okay, this is 2 columns. We know that y does not belong to the column space of H. Graphically, what does that mean? It's outside this plane. It's not on the plane, so y could be somewhere here, right? So Let me write, okay? Least square solution tries to find the theta IOS hat to minimize y minus h theta. Okay? Huh. Square, oh sorry, there's h theta squared, okay? As you change theta is your variable, okay? As you change theta, you can cover almost all the points on the column space of H, right? So as you change theta, there will be something like, this will be H theta 1, this point may be H theta 2. You can cover all the points on the plane. That's the definition of the plane. It's a linear combination of the columns of H. By changing the linear combination coefficient, you can sweep over all the possible points on the plane, but no such a point agrees directly with y because y is outside this plane, right? So what would be the best solution? Suppose will be something like projection of y onto that plane will be your best solution, y. The simple geometric intuition you have, right? So this will be your error. That error will be the smallest. Because if this is a perpendicular, if you find any other, this theta 2, then this will be your error vector, right? Error means y minus that, y minus this guy, that will be this line. So if this is the solution, so this guy should be our least square solution geometrically, okay? So I will say intuitively, H theta least square hat should be the projection of y onto the column space of H. That's my intuition. Hopefully that's somehow aligns with your intuition as well. You should be able to speak out your intuition mathematically, because whenever this is perpendicular, it's the shortest distance between y and the plane, right? Any other point on the plane will have a larger distance with y. Okay, let's check. We need to verify, okay? Let's verify our intuition. So let's verify our intuition. Let's verify our intuition. How to verify that? With so the error has to be perpendicular or orthogonal to the plane, right? So the error vector, which is y minus h theta hat least square. This is our solution, right? That solution has to be this guy, has to be this point. That means this will be this is our vector, error vector, y minus this point, right? That's our error vector. Error vector should be perpendicular, should be orthogonal, should be orthogonal to the column space of H. i.e., mathematically, that means what? Y minus head least square, okay, that's particular theta, has to be orthogonal. So the inner product with any point on the plane has to be 0. Any, not 1. Okay? How do you represent an arbitrary point on the column space of H? So H times arbitrary thing, right? Let's say beta. Okay? Well, I can use theta as well, but just want to not. H times beta for some beta will be a linear combination of the columns of H. So this guy will be a generic point on the plane. Are you with me? Has to equal to 0 for any beta. Okay? Of course, if beta is 0, it's always 0, but for any beta, it has to be true, then that's orthogonal to that. Let's check. Let's check whether this is the case. So let's plug in. So what we have is, okay, let me skip to the next one. So y minus h times least square. So h transpose h inverse h transpose y. Take a transpose times h theta. Oh, sorry, h beta. Okay. That's our, so I need to say this guy is 0 for any beta. If that's the case, then our intuition is correct and the solution is correct. Okay, so let's multiply this out. Will be, if you take transpose, will be y transpose, if you start from backward, from the end, y transpose h transpose h inverse is a symmetric. Okay, if you take inverse, it's also symmetric, so this is the same thing, inverse and h transpose times h beta. So that's, sorry, that's my first times this. Sorry, I forgot the first term. Let's put the first term. First term is y transpose h beta. This is minus y transpose h, this guy beta. Okay, so what you see is that this guy multiplies identity. Y transpose h beta minus y transpose h beta. Magic happens. It's not really. It's 0, okay, so for all betas. Our intuition is correct. So y is the projection, sorry, h, this guy, which one? H times theta b square is the projection of y onto the plane. Theta is not, okay? Theta is not. H times theta is the projection of y onto the plane of H. Is this useful? No, it's just somehow connect different things, but somehow this is can help you picture the solution. You're just doing projection onto the plane. So next time, when you see this thing, okay, y minus a theta, and you're trying to find bad theta, you will say, oh, that's just want to project y onto the column space of H. You can say it to other people. They may admire you, but you feel that's easy, right? It's nothing to be admired. H times theta is linear combination of columns of H. If you remember that, everything else should follow. So it's almost like an exercise of what we emphasize, linear combination, linear combination, linear combination, okay? That's the key for linear algebra. Okay. We have enough analysis. Let's go back to our example. We almost finished the first example. This is a line fitting for a few data. I want to fit a line with the data. You may want to fit other things for the data, but I propose this is a line. I want to find best linear relationship between x and y. And the last time we mentioned this can be formulated as a least square problem. Not only least square, it is a linear least square problem, right? You see how it can be done. So then in this case, in this example here, let's define this as y. So y equals to what? y1, y2 up to y5. What is y1, y2? These are the points, right? So it's 1.4, 1.2. If you like numbers, I can put them in, but that's not essential. Negative 3.6, 6.8, 4.5, that's your y vector. And then you have H matrix, also have some numbers. Okay, it's x1 up to x5 and 1, 1, 1. So it's 1.5, negative 2, 3, 2.5. This is 1, 1, 1, 1, 1. Okay, is H full rank?
Yes.
H is full rank. Okay, so H transpose H is also full rank, so we can take inverse. So in this case, my least square estimate, which will be my what? Alpha least square estimate and the beta least square estimate. These two are my parameters, equals to H transpose H inverse H transpose Y. Do you know how to compute this?
Yes, but slower.
H transpose H, these are all numbers. You know how to compute this. I will never test you how to compute, because whatever calculators can do, I don't think you need to do that seriously. So occasionally I need to, maybe in the exam I can ask you to write down the final answer. Maybe that's only worth a 0.5 per point. Okay, if you write like this, you got 95% of your solution. So that's how you formulate the problem is more important than how you calculate the final answer. Okay, so that's always my rule. So in that regard, I wouldn't compute this for you. You can try to compute this at home. Okay, once you compute these numbers, you will find two numbers, right? I don't know what these two numbers is. So that will give you the line. Supposedly, you can check, actually, that will fit almost the best amount of data. Okay, in this case, I may ask you, in this case, if y belong to the column space, in this case, is y belong to the column space of H? Can you see? Is y fall into the column space of H? It seems not, right? That means there must be some error. Okay, what you're computing is a projection. Can you imagine a case where y, for the line fit example, y falls into the column space of H? I will say, let me say this. If, let's say, your data agrees completely with your model, so this is just a line. Every point, oh, sorry, my drawing is bad. So this is a line, your data is like this on the line, so the error will be 0. You can check in that case y fall into the column space of H. I mean, you may find, you may have perfect data, just a line, all right? And in that case, you can find 0 error. There's no residual, okay? You perfectly fit a line, but that's typically not possible. In this case, that's, now I want to emphasize model, all models are wrong, right? Some are useful. That's the thing I mentioned to you before. You may think, I want to fit a line, but some people may think, I think the data is not a line. It's this exponential. So now I want to change that modeling hypothesis. I want to say, can you find the best, let's say use the same data. So those are the same data, okay? Same data, find the least square solution, estimate, find the least square estimate for A and B here. And I assume y is approximately b times exponential ax. I want to fit an exponential. There's a scaling factor b. There's also a exponent term a here, okay? Can we do least square? Not directly. Okay, so now in this case, theta is a and b. Okay, we want to assume b, the model assumption is b e to the ax. This is a nonlinear, you can use nonlinear least square. Still try to find the distance between, the minimum distance between y and the model predicted output. But if we take, in this special case, okay, if we take a log on both sides, you will have log y approximately equal to a of log x. Oh, sorry, ax, not log anymore. This log means natural log, okay? So you typically use this as natural log, right? But I'm adopting MATLAB notation. Log means natural log, okay? So that's ax. Agree with me? Now I'm asking you, can you use the least square to estimate the best a and b? Not directly, but you have to change variable. Okay, in this case, you have to change variable. So let's write down the measurement equation so that you can see it better. So we have a few data, right? So we have log y1 should be approximately equal to log b plus ax1. The data involves x and y at different sampling times, right? So log y2 approximately log b plus ax2. You have up to log y5, we have 5 data here, log b plus ax. Okay, so let's call this guy log b c. All right, let's define c equal to log b. Okay, c is unknown, b is unknown, so log b is c, so they are 1 versus 1 almost. Okay, so overall you will have, just excuse me for 1 minute, log y1, log y2, all the way to log y5 equal to, now it's linear in A and C, not in linear in A and B, okay? Linear in A and C, so the x1, x2, x5, 1, 1, 1 times A and C. Okay, so it's H. So that will be my, I call this guy my Y tilde, this guy my H, this guy my theta tilde. Okay, so I can find theta tilde least square equal to H transpose H inverse H transpose Y tilde. But this guy, you can find A least square and C least square. And this guy, based on the C, you can find B best estimate E to the C least square head. C is log B, B is exponential of C. Okay? So that's how you do it indirectly. That's one way to do it. You can estimate, but you can directly use nonlinear least square. That shouldn't be a problem as well. But this is one typical way of turning nonlinear problem into some problem. You can turning it into a least square problem, linear least square problem. Okay, okay. Let's take a break. Okay, let's get started. Let's continue the discussion now. We have been using the same set of data to do a line fitting and exponential fitting. The data is the same, it's your model is different. I want to go back to our original formulation, which in this case, we are picking different G. We're assuming different G structure. Okay? It's up to you what you believe is correct, but once you believe that, best parameter can be estimated using least squares. Okay, now let's do one more. Okay, let's say now I want to assume it's a quadratic function. Can you see that? I think it's not a line, it's almost like a quadratic like this. Is that fine? That's a valid assumption, right? You can argue that way. And if you assume quadratic, then your model and the relation with your data is like this. Okay? So that's your measurement equation. And now I want to say, how can you find? So the same data, find LS estimate for alpha 0, alpha 1, and alpha 2. That's fine, right? How to do this? Is this a least square problem?
Yes.
It's become nonlinear. Why is it least square? Is this least square? You think this is least square?
Yes.
Yes, why?可以用汉语。It's hard to see now, right? But as long as the measurement equation is linear in the parameter, you're fine. I don't care whether it's nonlinear in X or not. It's just, it's linear in the unknowns you want to find. It's linear in alpha, okay? So that's least square, a linear least square. So let's say theta equal to alpha 1, alpha 0, alpha 1, alpha 2. Let's list the measurement equation, right? So we have y, we have how many measurements? 5, right? y1 should equal, according to this equation, y1 alpha 0 plus alpha 1 x1 plus alpha 2 x2 squared. Okay? If my model is correct, that's the relation. And the y2 alpha 0 alpha 1 x2 plus alpha 2 x2 squared. Then I have y5 alpha 0 alpha 1 x5 plus alpha 2 x5 squared. Are you with me? At least a bunch of measurement equations, that's my assumption. Okay, of course, in reality, they won't be exactly agree with them. If you want to write very carefully, you have to have some noise term out there, okay? But that's, I assume you're clear with that. So in this way, I can argue my measurement equation is y1, y2, y5, that's my y vector, okay? What about this? I need to write it in terms of a linear mapping of theta, which is alpha 0, alpha 1, and alpha 2. Can you tell me the first, this is alpha 0, alpha 1, alpha 2. What's the first row? Plus v, okay? It is 1, x1, x2 squared. Oh, sorry. This is wrong. Okay, you should correct me. That's confusing, right? The first data point, x1, raised to the power 2. Okay. What's about the second row? 1 x2 squared. The last one is 1 x5 squared. Okay, that's it. So then we have this guy is our H matrix, theta. That's a least square problem. You plug in formula. That's your favorite step. It's plug in formula. You write it down. H transpose H inverse H transpose Y. That's it. And that will give you 3 numbers. That 3 numbers is your best estimate, best quadratic function fitting for this data. You can do polynomial fitting. You can do whatever fitting you want, as long as it's linear in the coefficient. You have a least square problem, right? In robotics, there's a lot of polynomial fittings, so they all can be turned into least square problems. Any questions so far? I hope you can imagine this can be a rather complicated things, this relation. Actually, if you have one layer neural network, that can also be written as a least square problem. It's just one hidden layer, okay? Because it's the sum of weights times the hidden neuron activity function. That function is nonlinear, that's fine, but it's a linear weighting of them. So you can identify one layer neural network is also fine, but not deep learning, then it's won't. Okay, it's become a nonlinear optimization problem, non-convex. Okay. All right, so that's enough for the examples. We learn this least square not because we just want to learn it. We want to know how we can use it to identify the parameters for our model. Our model is dynamic model. It's described by differential equations or difference equations. All can be turned into state space form. Okay, we know how to change among those forms. So let's see how we can use it to do system identification for linear systems. Have you heard about this autoregressive model? Autoregressive, 自回归 signal system. You have filter, right? You have IIR, finite impulse, or infinite impulse response. I forgot what it is, okay? Anyway, these kind of autoregressive models are very common to see in data analysis. That's also a common way to write down the linear difference equation. Okay, so this is nothing but a linear equation. So let's assume we have ARX model, so autoregressive with exogenous input. This is the autoregressive term. 你没学过这个什么回归，自回归项什么这种没有对吧？
学过好功能。
这种形式看过吗 ？YK 这种 ，YK 加上 something times YK minus 1， 见过没有？没见过。看过。OK， 没给它定个名词而已，对吧？这倒无所谓啊。没见过它，今天就见了，好，可以吧？已经见到了。Autoregressive term. What does that mean by autoregressive? It's depend on itself. Regressive is past. Okay, auto depend on itself. So it's 2 terms. Okay, this term is almost like if you do signal system typically, this is almost like a moving average term. Moving average. So the output is a moving average of the input. That's kind of a finite FIR type of filter. Autoregressive depends on history. Okay, anyway, we can just think about this as a generic way to write down linear difference equation, right? So that's typical the way to model discrete time linear systems. Okay, in this case, if we have such a model, we can turn it into transfer function. We can also turn it into state space models. Okay. So for the model parameter, in this case, what are the parameters? Those alphas and betas are all parameters. Okay. So I want to say, suppose if my model is yk plus yk minus 1 equal to 2 uk minus plus beta 1 uk minus 1. Suppose I have an equation like this, that's beta 2 uk minus 2. Theta would be what? One way to copy this guy will be what? 1, 2, beta 1, beta 2, right? That's one way to copy, right? That's, yes. Okay? But I want to say this is wrong, okay? Theta only contains unknowns, okay? In this case, theta is still beta 1, beta 2. That's our correct theta. We will see how it works. But picking theta means picking something unknown. If you already know the parameters, that become part of your data, part of the known part, okay? It's not the unknown. Theta only contains the unknowns. Okay, so how do you evaluate which set of theta is better? Whether this set of data, the parameter gives you good output prediction, aligns well with your data, right? So that, in other words, it predicts better. So this guy is basically a prediction model. You use your current input and the past input and output data to predict your next yk, okay? Suppose you're at the k minus 1, you use all the information you obtained up to k minus 1 to say, okay, I think yk should be satisfy this, okay? And then you take a measurement, you see yk is something else, and you want to minimize the error. Okay, so this is one-step prediction. This is given, let's say, given the parameter theta, we expect the model expect, okay? The model expect to see or to measure or to see an output measurement. Output measurement y given theta. Okay? So what your prediction is depends on what theta you pick. Different theta gives you different prediction, and you want to find theta minimize the discrepancy between your data and your model prediction. Okay, so given these data pairs, I want to find parameter to minimize this cost. Let me do some change. Let's see, sorry, this guy should be theta. Let's use theta. Okay, so J of theta is my cost function. Summation from k equal to 1 to n. Y hat, k given theta, minus, I just want to be consistent with my notation before. Hat is something estimate. That's what I see. That's my model tells me what to see. Okay? Good theta should minimize this discrepancy, this error. Okay, let's see how it can be formulated as a least square problem. Let's see, let's direct jump to the formulation part. So regressor, let's say at time k, Suppose I'm currently at time k. Okay. My predictor will say, okay, I expect to see yk hat given, if you give me a theta, I would expect to see this kind of yk hat. What is it? If you look at the model, yk should be minus alpha 1 times all of this plus the beta, right? So if my model assumption is fixed like the autoregressive model, so I'll have alpha 1 yk minus 1 minus alpha 2 yk minus 2 dot 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 minus alpha what? Suppose I have p terms, right? This is an autoregressive pq. I have a p all regressive term backward in times p, and the moving average term back in time up to the last q steps. Okay, so in this case, I will have alpha p yk minus p plus beta 0 uk plus beta 1 uk minus 1 all the way to beta q uk minus q. I use my past p steps of output and past or previous q steps of input together. Actually, is the linear combination of them, right? To predict my current input. So my current input, you assume that, okay, from previous input output, it's a linear combination of previous input output gave my current output. That's the model assumption. Okay, is this linear in parameter? That's my question. Now you should be very sensitive whether something is linear or not. And linear in what? Okay, it's linear, so we can write as a y matrix times vector. In this case, just one row. Let's say this will be my y minus yk minus 1 minus yk minus 2 minus yk minus p uk plus 1 all the way to uk, minus 1. Thank you. Minus q. Okay. Times a big alpha 1, alpha 2, alpha p, beta 0, all the way to beta q. That's my theta, if you remember, right? So my prediction y relate to my parameter linearly, and the linear relation is captured by this particular data vector, okay? And I can give this data vector a fancy name. Do you know what it is? This is called a regressor. It's just called a regressor at time t, k. Have you heard about regressor? 回归那怎么翻译我不知道哈。Regressor. Let's define it as what? Phi transpose k. I hope you're fine with notation. This is already minimum. What is phi transpose k? Is this entire row of data. Okay, it's constructed by data from the past, right? So in other words, this will be phi transpose k, take the transpose times theta. Okay, a row vector times theta. So keep in mind our data, depending on how you number them, we always start from some initial index. That's a U1, Y1, U2, Y2. So note, let's say for phi transpose k to be well defined, we need K bigger or equal to max P and Q. Okay, if you start from 1, right, your data start from 1. So you can start having this relation for K bigger than P and Q. Otherwise you have negative data that are not available with this, right? Depending on how many times you want to look back, you should start. You need to first use the first couple of steps, couple of data points to define this regression. Okay, you will see that clearly from the example. Okay, so let's say let's denote K0. That's our first available relation. Will P max P and Q plus 1. Okay, suppose that's. Then start from K0, I can list all this. I have all the data I need to construct regressors. So it's Y K0 is equal to phi transpose K0 theta, okay, plus noise. That's my first row. And Y K0 plus 1 is phi transpose K0 plus 1 theta plus VK0 plus 1 dot dot dot. Can you tell me what is this phi 0 K0? This is my shorthand notation, right? What is this one? It's just a row vector of this form where you replace K with K0 plus 1, right? Okay, I think you're fine with it. So it's what? Minus Y K0 plus 1 minus 1, which is Y K0. Sorry. Yes. Okay. Minus Y K0 minus 1. All the way, okay? I don't want the list of them. It's just a time shift. So overall, you will have the following terms: YK0, YK0 plus 1, all the way to Y of M. Where does M come from? The number, this M is the number of data points, right? Data pairs. This is M. So up to M. Okay. So then you have phi K0 transpose, phi K0 plus 1 transpose, all the way to what? Phi M transpose theta plus V. That's our Y. This is our H. I have a theta. It's all the coefficients. So my least square estimate for this autoregressive coefficient will be H transpose H inverse H transpose Y. Okay, I think you should be very familiar with this. Any questions? Let's look at the example. The example you may see in reality or not, but typically you could. Suppose you have a transfer function. That's why I want to review the transfer function last time, right? So suppose you have a transfer function. Okay, we want to build a transfer function, but the transfer function involves some unknowns, which is A and B in this case. I want you to find the best estimate for A and B given the 20 data point. You take a measurement. Suppose you're a student, right? You collect data, and then graduate student tell you how to do the estimate. Okay, they publish papers. But suppose now you want to do it by yourself. You collect 20 data points, and we're asking you how do you fit the best A and B? What do you think? So you have g of z, that's your u, that's your y. And you collect input of data pairs you want to compute or find the best estimate. Okay? And the first step, let's find the corresponding ARX model. All the dynamic system is difference equation. Okay? You can transform them to z domain, become transfer function. But it's equivalent, you can move back to autoregressive model. So let's say g of z is, let's divide it both from the numerator and denominator by z cubed. So I'll have z inverse plus, if you don't divide, you'll have yk plus something. I want to have it backward. So this is b3, 1 plus a z negative 2. Correct? Okay. What does transfer function mean? yz equal to g of z times u of z. If you multiply, you got what? 1 plus a z minus 2 yz equal to z inverse plus b negative 3 uz. You take inverse z transform. You don't have to, but you can see it already. So this is nothing but a time delay, okay, depending on how many steps you delayed. So this will be, in time domain, this will be yk plus a yk minus 2. You assume 0 initial state, okay? That's for Z transform. So this part is uk minus 1 plus b uk minus 3. Okay, that's basically a delay relationship. So Z inverse is a delay. If you use MATLAB Simulink, you can see that directly. Am I right? So I'm going to ask you, this is ARX what? What is P? P is how many steps I look back for the y term. It's 2. What about Q? 3. Okay? So I can start to having valid data after 3 steps. So I will begin with step 4. Okay? So K0 is 3 plus 1 equal to 4. Okay? If I write it down, you can see that, for example, this y4 should equal to what? Negative a y of 2, okay, plus u of what? 3, plus b of u of 1. If I start from y3, then I have to use u of 0, which I don't have this data. Do you see what I mean? If I start from y of 3, then I have to use u of 0, which I don't. My data start from u1. Okay, how do we use the data? What is our theta? If you look at this autoregressive general model, you have all the parameters you need to fill in, but some of them are known, right? For example, beta 0 is known here. These guys, yeah. So many terms is known, so you don't need to put them into the theta. So the only unknown is A and B. And my purpose is to write the equation linear in the unknowns. So I will propose the following is y4. What do you think? I should move this u to the left. minus u3 equal to negative y2, this u1 times a and b. Okay, I always like to see this. Everything known should be moved to the left. Okay? The right-hand side only involves unknowns, and that unknown should also be a linear function of the parameter theta. So plug in the formula doesn't work in this case. You have to do some changes, okay? So essentially what we have is the following. It is y4 minus u3. This is y5 minus 4, okay? All the way to y, how many data I have? 20. I have 20, right? Minus u19, okay? I have a big column vector. And the left-hand side, I have a matrix. Okay, this is negative y2, u1. The next one is negative y3, u2. All the way to negative y18. This is u17. Okay, so times A and B. Now you should know it. This is our y vector. This is my H matrix. This is my theta. Are we good? So do I need to write it down? Theta least square hat H transpose H inverse H transpose Y. You should forget about this formula, but somehow you can remember it now. But that doesn't matter. I don't care about this step. I only care up to this step. So whenever we give a test on least square, some people spend a lot of time computing these numbers, which I don't really care. If your H matrix is wrong, then your formulation is wrong. And no matter how many time you spend on calculating this, it doesn't bring too much intelligence, okay? So you have to know how to formulate this. This is okay, right? I have another example which is similar. I don't want to go through them. I may write it down later after class and upload the lecture notes, so you can take a look if you want, okay? So now it's already done for linear least square problems. Some people may ask, what about state space model? If you find a transfer function, you know how to construct this state space model, okay? That's the way it is. And we don't know, we don't learn the general way to identify state space model. That's a little bit more involved. But I think this is enough for most of the application you care about. Okay, now let's do some fun stuff, which is nonlinear least squares. This does not really directly relate to linear system theory, which is the main focus of this class, but it's very important. And I think I just have 2 slides to briefly introduce that to you. Then you know what to do if this system is nonlinear. The problem setup is the same. Under what condition this is linear? Yes. So typically this guy, so as what we see, for example, in this case, this will be our g theta, okay? It's equal to h times theta, right? That's our g of theta, the model predicted output. It's a function, linear function of theta. But oftentimes, it could be a nonlinear function, right? So g theta is a linear least square if g theta equal to h times theta, right? Otherwise, it's nonlinear. Nonlinear, otherwise. Okay? But the same principle applies. What I should find the best theta for? The theta should minimize this cost function. Okay, I think this should be the mean of theta over theta. Okay, numerical optimization algorithm can be used to find optimizers. Okay, so I just need to find the optimization algorithm to solve for this. I mean, the same principle applies. It's just instead of have an analytical solution, you may have to use numerical packages to solve it. Okay, in MATLAB you have fmincon, but in Python we're switched to Python this semester, and there's also other optimizer functions. SciPy has a SciPy.optimization or optimizer. You can use that to find the optimal solution. Of course, we are not trying to teach you how to program a optimization algorithm, but there's so many different packages you can use, which will be much better than your own coding. Okay, it's a professional. That's it, nonlinear least square. Let's see an example. I don't think you get it yet. Navigation, this is more a toy robotic example. Navigation by range measurement. What is the range measurement? You can only measure the distance, right? You only know how far it is away from me, and you don't know which direction exactly. It's just the range, okay? So what are the sensors give you range measurement? UWB? Yeah.
But somehow we have
Okay.
here.
Let's just, yeah. For example, UWB. That's only a range measurement. Okay, you only know, okay, there's 10 meters away from me. Okay, but you need several of those things to triangulate to help you figure the measurement is. Okay, in this case, suppose this is my target, right? And I have a few what I call beacons. Okay, so I need to know where they are in the environment. I need to put my UWB in this corner, that corner. I need to know exactly where they are. Okay, then I use this guy's location to triangulate or to find my target. Okay, so those P3, Q3, P2, Q2, those are known. And the unknown is this guy. Is the unknown, this guy is theta. All right, I call the theta 1 and the theta 2. That's the planar location of this target. Target location is theta 1 and theta 2 is 2 coordinate. I need to estimate. Whatever unknown, I'm trying to use theta, but in reality, there will be x and y, right? What you can measure, the distance from the beacons. And typical assumption is that will reach to the beacon location. So the S measurement will give you S beacon's distance from the target. And plus some noise, you'll never be exact. Okay? What do you think this guy is? This is square root of B is 2 coordinates like this. So Pi minus theta 1 squared plus Qi minus theta 2 squared, right? Plus some Vi noise. If this is linear in theta 1, theta 2, I can use the previous formula. But in this case, it's nonlinear, right? It's highly nonlinear, so I can now use it. So what we should do? We need to still form the cost function, it's the same. Given the measurement, I have a few measurements. Find the best target location can be formulated as a least square problem. So we just need to choose theta, minimize this. Does this make sense to you? What we are trying to minimize? This is my model for the ith measurement. So if my model is correct, it will tell me, okay, this is 10 meters from the data, okay? But when I see, so if this is the location, that will return me the true distance from the beacon location to the unknown target location. But I see something measurement y, I want to minimize the discrepancy between them. I also want to sum over all the possible measurements I have. So in this case, I will say nonlinear least square head is, I will use this shorthand argmin j of theta over theta belong to capital theta. What does this argmin mean? The minimizer of this cost function. Okay? Whatever that is, that requires some numerical algorithm to find it. If you want, you can take other class to teach you how to write down those optimizers, write these optimization solvers. But in this class, it's fine for us to use existing ones. Coding example. Okay, let's go back to some code. So in SciPy, the optimization, there's a SciPy.optimize package. There's different solvers. There are even least square solvers directly, but I prefer you to use the minimize. That's almost similar to the fmincon in MATLAB. You can solve arbitrary numerical optimization problems. Someone you may solve it correctly, someone you may not find the best one. Okay, you may stuck to bad local minimum. So I'm start using this deep node. I'm not sure whether have any of you tried this. I uploaded a video before deep node. If you haven't shared, okay, but it's very convenient. I'm not sure whether I'm connected or not. So it's just Jupyter Notebook, okay? So let's see. This is nonlinear least square problem. Oh, I haven't turned on my computer yet. I need to start. Remotely, they will start a machine for me. Setting up hardware, I assume you can see it.是不是现在用的人太多了？你看。Okay, ready. So all I import is numpy, import random. Numpy is numpy. I import some plot function. Okay, I run it. Control enter. The package are run. Okay. What I'm doing is exactly the. Let's look at this part first. Okay. So B is my beacon location, and I put all the beacon locations as columns of B. So this 1, 3, 2, 2, I have how many? Depending on the number of columns. 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 beacons in the environment. Each of them can tell me how far the target is away from me. Okay? Then I randomly select the number true position, which is 4, 0. The true target is at 4, 0. All of these beacons will tell me how far away they see the target. Okay? Then I can try to draw this thing. You see there's so many beacons. Those are dots. This is my target position. Okay? And each of them will tell them the measurement. In reality, you will directly have the measurement, but in example, we somehow have to generate some fake measurement to try, all right? Now for testing purpose, let's generate some data. This is random noise data, okay? And this is the variance of the noise. So the measurement have some noise. Okay, y is 0, and then I have a measurement, which is the true distance. Can you see that? The true position minus bi, that will be the true distance from the S beacon to the target, plus some noise. Of course, you cannot have perfect ones. Okay, so in this way, I generate some measurement. Then I initialize my initial guess at theta 0. Okay, then I call the optimize.minimize. Minimize what? A cost function. All right, with initial guess and with additional data parameter I need to pass to the cost function. Then I find the solution. So now the key is that what this cost function is. The cost function is this. Your measurement, in this case, is you generate your own measurement for testing purpose, okay? And the model, if you give me a theta, I will tell you the true distance, okay? So I need to sum all of these error terms together. That will be my cost. This function was written here. Okay, if you can you see it? This part, okay? So it's define nonlinear cost function. Theta is my unknowns, all right? I want to optimize. B and Y is some additional parameter I need to send to this cost function to evaluate its cost. Initially, J is 0. Then for I in the range of B, so basically the number of beacons, okay? So yi minus the norm between theta and the B. The current beacon's location is the true distance, and the yi is the measured distance. Their discrepancy is the error. You take a square, that's the error. You add to the total cost, and the sum over all the things, okay? The reason I put an item here is that this is an array, and the cost function requires scalar. I think Python earlier they have add scalar function, but now they don't. So I'll just call it item 0 to return a scalar of the cost. Anyway, so I can run this part, run node, hold on, control enter. It's done. So the function is defined. Now let's look at this part. I can estimate. It's done, okay? Let's see what is res. So the rest is the result from the optimizer, okay? It tells you, okay, the optimal cost function is 59, and the optimal solution, where's the optimal solution? X is the optimal solution. It's not 40, okay? It's far away, and you can test it. This is the true target, this is your estimate. It's far away because your noise is very large. Your noise is almost very big. So if you reduce this noise by half, I think that should be closer. Still that. Let's see. Okay, you can play with it later. Okay, that's it. I think我们会发一个今天或者明天吧，发一个 project 啊 ，project 也是国庆过后的一段时间丢。